Hello everyone, and we're back again on AtCoder, again here on the beginner contest, this time 312. As always, as usual, we do this every week. Sometimes I skip it if I think maybe there's nothing much educational in it, or I solve just to like task D or something, task E maybe. Then yeah, so check out the other channel, the other content on my channel as well, not only like the screencasts but some other content. We usually succeed solving a lot of these problems, but yeah, we'll see how it goes this time. Yeah, so don't forget to subscribe. Always click that button. I mean, it gives me the motivation to keep on recording this because I don't get any money out of this, so it's yeah. Okay, so task A, given length 3 string, print yes if it's equal one of these, print otherwise no. So what I will do is when I see when I see something like this, I can just copy these, like whether or not, and what I can do is I can put them in some array. There is find and replace feature you can use for this, but this is fast enough. Then I can iterate over, I can read my string. I always use capital letters for the inputs. So if a of I is equal my string, then print yes. Otherwise print no. Of course here just return 0. Oops. I have like this specific style of using like specific camel case, or I don't know what is called, but it doesn't matter. Okay, task B. Hashi invented tag code, two-dimensional code. It's a region consisting of 9 horizontal and 9 vertical. All 18 cells in the top left and bottom right, 3 by 3 regions are black, so all the 14 cells that are adjacent horizontally to the top left and bottom right 3 by 3 are white. It's not allowed to rotate. You're given a grid, the state is described like this. Find all the 9 by 9 regions completely contained in the grid that satisfy the condition. So one of the condition is so what is the output? The out for all pairs one is a region, because these here, and then we have all of the whites here, and this is again, yeah. So this is how a region should look. Okay, just simple brute. Oops, not Rust. I don't care about Rust. There's no test cases. Simple. I will have a vector of strings. Then read these strings. Just make some space like this. And then so it's 9 by 9 always, right? So I start from every point, then I go 9 so this is 9 by 9, but here I will say this is minus 9 plus 1, minus 9 plus 1, I think. Is there, okay, there's no case like this, but whatever. So you have to check that all of the 3 by 3s here first yeah, so 3 by 3 here I will check that all of these are that. Also I need to check that all of the last one, so here that's like plus 9 minus k minus 1 plus 9 minus L minus 1. These are also, and then you need to check that like these here that are also like this. So to do this I will check that I will do 4 by 4, but I will do it only if k is 3 or L is 3, then I will do this. This will just eliminate that I don't. And then if it's okay, then I will print do you need to print it sorted by sorted something? So this is n minus n minus 9 n minus 9 and just print where it crashes. It crashes when it comes to Wait, so this is if n is 9, then 9, yeah, that's correct. So that should be correct. Let me just add a new test case. where this is 9, 9, and then let's fill up this. Is that 9? Yeah, that's 9. So 4, 7, 9. Okay, so let's just print -1 here. Okay, that kind of works. Wait, why that doesn't work? How is projected n strings? Yeah. So I plus. Yeah, that's correct. Then this here is also minus L minus 1. That's correct as well. Yeah, of course, this is not finding because this has to be dots. Stupid mistake, okay. Okay, see, there are n sellers and m buyers in an Apple market. The ith seller may sell an apple for AI yen or more. The ith buyer just the ith buyer may buy an apple for bi or less. Okay, find the minimum integer x inside the condition number of people who may sell an apple for x yen is greater than or equal. Find the minimum x such that, okay, so can we binary search over x? So if x, or no, wait, who may sell for x yen is greater than or equal to the number of people that may buy. Can we binary search? The condition, people who may sell an apple for x yen. The more, so yeah, so that's the, yeah, so that could be binary search. Yeah. Is it always? Yeah, it's always possible, right? x is like, okay, we binary search over x, so it means like it's 10 to the 9. Int cell by. Now, you technically don't need to iterate here, but you could do it in log time. But since this is fine, I will just iterate them. Sell an apple for AI yen or more. So if sell would be plus equal if mid is bigger than AI. Buy would be if mid is smaller. If buy is smaller or equal than BI, then if sell is bigger than buy, we want to say that R is greater than or equal. So if the selling is greater than or equal, we can just move R to the mid. Else we can move left to the mid. And then we just want to see out R because R is valid. D, you are given a non-empty string S consisting of opening, closing, and there are 2 to the x ways to obtain a new string by replacing these characters with some other strings, some other brackets. Among them find a number of ways it will yield a parenthesis string. A parenthesis is a string that it's so parenthesis is like a valid string, right? So this here goes up to 3000. So it means it's like a DP. Okay, so replace the number. There are 2 to the x ways, where x is the number of occurrences here. Okay, so this is a little bit difficult problem. If I'm here, the balance dp of I and balance, if I'm here at position I, and there is a question mark, I can put a bracket opening or a closing bracket, thus getting the balance down or up. But I cannot ever go a balance under 0, so this is the idea. So I need to go over all of these. Say first that like dp of 0 of balance, so let's say like this. So if 0 is like an opening bracket, then dp of 0 balance 1 is like one possible thing, right? Else if s of 0 is like a closing bracket, then this is not possible, because we're already in a negative balance. Else, so it's a question mark, that means that dp of 0 1 is 1 again. So yeah, so that's that kind of like, just so essentially we have to do this, but we can just test for this if that's closing, then and then you iterate from 1, and then you iterate for the balance, which goes from 0 to some, let's say 2 to the n. I don't think you can achieve more than that, but even if you achieve that, you don't quite care. And then dp of if s of 0, if s of I is equal to like an opening bracket, then all of these balances, so dp of I, dp of I balance is dp of I minus 1 balance minus 1. And then the balance balance is bigger than 0. Else if this is a closing bracket, then we want to get this. Else if s of I is a question mark, then we want to get from dp I minus 1 b minus 1 and dp of I minus 1 b plus 1. This here is only possible if b minus 1 bigger than 0 is this, bigger or equal to 0, or otherwise is 0, and then that answer is dp of n minus 1 0. This is our answer. Just sorry. Okay, great, accepted. Tangency of cuboids. Okay, so there are n rectangular cuboids in three-dimensional space. These cuboids do not overlap formally. They're okay. Best intersection of value 0. The diagonal of ith cuboid is a segment that connects 2 points. So this is like, okay, so this, we know that this is the diagonal of the ith cuboid. For each cuboid, find the number of other cuboids that share a face width. Formally has a positive area. So okay, so this is quite a cool problem, actually. Quite a cool problem, considering that the cuboids are like this. So like you have some cuboid here and like some cuboid over here, right? Could be something like this, doesn't really matter. There's like some overlap, and there's like this diagonal of this cuboid, but this diagonal could be like here as well, right? So that's a one thing. Yeah. So, and yeah, you can have like this, and the idea is that on one of the directions, so either 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 x. So if I have the axis like this, let me just oops. So if I have the axis like this, such that this is y, this is x, and this is z, here these 2 points share the same y coordinate. But there could be a cuboid here that has this coordinate here, the same as this, so the same y coordinate, but now in the x direction is just way off. So one thing you have to do is to check for a pair for this coordinate. Is it inside the x direction? The z direction is like this, and the y direction, I mean the y direction is like this, but it doesn't quite matter because it's positive area. What about has a positive area? What about, okay, here's some, this is kind of tricky if there's no like trick involved with it. To code this is quite what about it's like if it's on the edge here? What about if this cuboid is such that like it's on the edge here, and his diagonal looks something like this, right? And now, does this cuboid have a positive area here of this face intersection? I would say no, right? But if I have only the bounds here to judge if this point is x, y, z, and like these are x1, y1, z1, and x2, y2, z2, then x is inside x1 and x2 because x is equal to, it doesn't actually matter, and this holds true but has negative there. So it's kind of tricky. It's okay. So we need, do we have to generate all of the faces and then see like that would be too much work, right? You generate all of the 6 faces and see like intersection on, how would you find quickly an intersection of these faces? That's an issue as well, right? Because they're 10 to the 5, and then you need to quickly say so what do you need to output? The answer for each I, find the number of j's such that the intersectional surfaces of the ith and jth cuboid has a positive area. Okay, so let me just take a look at clarifications. Print n lines. The ith output they contain the number of other cuboids that share the face with the share a face with the ith cuboid, but this doesn't, it has a positive intersection area. So a positive, if cuboids are on the edge, does that count though? Okay, however that might be, a positive intersection area okay, so for, okay, how do we search this? Okay, so we have XYZ, and we want to see if how many cuboids does it have such that x and y and z are in this range. So there's some range, there's some cuboid, there's some like thing. Then you need to find if a point is like inside that. Okay, so here the trick is that at most 6 cuboids will so my cuboid can touch on average at most 6. There couldn't be like a square, so yeah, so that makes sense. So is there a configuration that breaks that? No. Okay, so given these 2 points, I want to find which ones do I Interesting problem, I will say. Interesting problem. So because one cuboid can touch like on average at most 6 other cuboids. Yeah, there will be like some cuboid that touches more, but if this cuboid touches more, then these like are like already known common intersection. But still, how do we find out what is the best? This is XYZ. So my XYZ has to be in some range. So like what you're trying to do is you're trying to, what about given some range, some XYZ points, find each point that is like inside the range, and then okay, so we have some XYZ points, right? And then we want to find a point that want to find all points so let's say that okay so let's say that I'll go through each dimension and say that I will vary x, but y and z have to be equal, right? Is that correct? So now y varies. 1 is equal always, right? One dimension is always equal. So I will make first x equal, then y equal, then z equal, and then inside, if the points are x equal, then I have range, and then okay. So let's say let's say that I have some YZ range to some other YZ. So YZ1 here, and then YZ, Y2, Z2. So some range that X are equal in this range. There could be this point that two are equal actually, or more. Is that? That's possible if it's like on an edge, right? So like if it's on an edge, but I believe that because of the constraints that there cannot be ever quadratic solution, quadratic touchings, then you could just eliminate one of the points and then just go over now my problem is how do I find this range here, that like xy is cy and then this is one is equal and then the other can be valid. Okay, how do I query this? Like having a data structure that will y and z make so what does that mean? That means that, okay, so I have some graph and I have some rectangle, and so this is y z1 and then this is y2 z2. Okay, so we have done this. So we have some rectangle, and now we have many rectangles of this. We have many rectangles, and now there's some point here. Now I want to query, is it inside one of the rectangles? So how do you do this? You may want to like use some sweep line where like you sort them and then you go over and then you say, okay, but you answer all of these queries at once. That could be also the case. But wait, the points are very small. This is only very small. Thus I can iterate over. Wait, this is very small. This is very suspiciously small here. So the 3D space is at most 10 to the 6 voxels. So for each voxel, I have some points. I have some connections between these voxels. Okay, and now I have some connections between these voxels. And now when I have some other cuboid, can I somehow like sweep line this here, this whole thing? because it's very suspicious that they're very small. So you start from here, and then this will propagate up wait, I can divide the place into like three different planes, and then you could see that this X like projected this Y down here, and then you want to test out if this plane intersects with some other plane. So you have some like plane of this surface where this X is, and this is X projected, this Y projected onto this plane. And then there's some other plane, maybe like this, which intersects, and this maybe like this, some other X and some other Y projected. For all of these, you just want to find if there's some positive area intersection, right? And then like connect these two together that they're intersected. Okay, so I just divide the place like this, like on the 3 dimensions, and I have some rectangle intersection, and then rectangle intersection can be solved with some sweep line. But this is quite the problem to implement. Okay, let's go to F. There are n items. Each of these is one of a pull tab pull tab, a regular pull tab can, a regular can, and a can opener. Okay, it's described by an integer ti and xi. If ti is 0, is a pull tab. If you can get happiness of xi. If you obtain it and use a can opener against it, you get the happiness of xi. It can be used against at most xi cans. Find the maximum total happiness that you can get by obtaining m items out of the n. So there's some restriction on n. And then, okay. So the can opener is used to can open at most xi cans. So, okay, so that's kind of I don't know why I think of like of max it's definitely not max flow, but okay, so it can be used at most xi cans. If the regular can, if you can obtain and use it, get Okay, so there's something greedy probably here. Happiness of xi. If the happiness is bigger than the happiness Wait, you would only use the most... Well, you would sort the can openers, right? So you would get the can openers and you would sort. If you buy a can opener, you will buy the most powerful one. Then with this can opener, you can open the regular cans and at most this many regular cans and get like a very large happiness, right? So theoretically we want to somehow, do we buy a can opener or do we don't buy a can opener? Okay, so sort the can openers by the number of cans they can open. Then you do you sort the regular cans by the happiness, and you sort these cans by the happiness. Okay, and each can opener can open some amount of regular cans. So these are sorted like this in happiness, and these like in this can opener. So this is opener, and this can open the most cans. And we will definitely, like, if we're buying this, we're definitely gonna buy this one, and then we're gonna buy this one to open like not that important cans. We're not going to buy like this, which has like 2 cans only. There's no sense to buying this. You can buy this. So definitely this will be like that. And then let's say this has only 1 can. Then let's say there's multiple more cans like that. And then there's some other cans that can also like be both, but like has some like in between happiness. Let's say that this can is here and this can is here, and like some other cans that are just like these pull tab cans. Okay, so these are pull tab cans and these are regular cans, right? And now you want to say that, okay, if you're buying this, then I mean, now I have M items to buy, right? So how would you go about buying this? Of course you could maybe do some max cost, max flow, but this is not the point of the problem. The point is like, okay, getting this opener, and then I mean, if M is 1, I will get this. But if M is 2, I can get this and this. If M is 3, then I will get these. And if it's 4, I may get this, this, and that. So it's some kind of... It depends on like... But it is greedy. We will never get D. We will never want to pay these. Okay, so it's greedy, but how do we know which one we want? Well, we can maybe sort them and go from here and then say, okay, we kind of want to get this guy, right? But I don't know if M is enough. So in this opener, this opener would get like this amount of happiness, and then if M is enough, then I will so I have to sort them like that. So Okay, so let's, maybe will be more logic, but it should be like this. So there's n and n here, and then there's like can openers, so openers, and then there are these so yeah. So these are cans. And then for each of these n, I get a type, and then if type is 0, which means that, no, if type is 2, if it's an opener, then openers push back, wait, I can just read x here as well. Else, now the trick here is that, okay, cans will be pushed back, and first we want to sort by x, but because it's decreasing and we want to prioritize a regular can, unless a pull tab. No, we want to sort first pull tabs, because pull tabs I can pay for them. Regular I need openers to do that. So I will do x, then t, and then I will switch it by 1. So I will just flip this t, and then I can sort the cans in decreasing order, and I can sort also the openers in decreasing order. This will sort first decreasing x, and then decreasing this guy t here, which means first we'll sort like first the pull tab and then the regular. Okay, and then somehow I need to now deal with this priority here. So I kind of need to go over the cans. Let's say, so I have some answer. I need to go over the cans and say that the ith can is a can opener. It can be used, no, not the, yeah, go over the cans and say first this will be sorted by x. So if it's of type, but wait, what about buying like 2 of these instead of a can opener? You could buy 2 of these, or many, or multiple of these instead of like this and a can opener. It's not that trivial actually. Okay, interesting. Interesting. What if I buy all of these pull tabs first, and then I have like some left over, and then I buy some of these, and then I say I buy like a can opener and then like some of these. Then I say, okay, what about if I exchange this like here, which is like very small, for like one more here, and I do this until I say that I cannot buy any more of these until I buy a can, and then I exchange this guy with a can. So yeah, so let's do this. So this is regular cans, and then you have some so these are like pull tabs, and then regular, right? If T is 0, pull tabs pushback. Else if T is 1, then regular pushback. Else can openers pushback. So what I can do is okay, I need to sort the openers in decreasing order. I need to sort these in decreasing order. Regular cans. And then I sort the PT cans in decreasing order. So. And then I need some pointers. I need a pointer here that will go and buy all PT cans. So buy M of the minimum of M and this. So this is like how much the minimum of M and this. And then you say, okay, happiness is PT at I. Okay, so you have some happiness. Okay, so this is at least this. All right, so at least this. Then there's something left over. Left over is M minus the minimum of M and. So this is left over for like the can and the openers and shit and like that. So I need to go over the R dot size, and openers is going to be for 0. If openers is 0, I need to buy an opener, right? So okay, so first of all, if leftover is either like if it's even positive, that's the thing. So, and I need to buy the opener, to buy an opener. So int opener pointer, this is pointer, and this is left. How many of this are left, and then I see, so what about if there's no opener? Let's say if openers dot, I mean the R here, what I can do is I can sort them through R, but then I can like R dot resize the amount of accumulate openers that begin openers n ll. So I can resize to the minimum of r.size in this. So this will say, okay, I will sum up these how many of the openers are, and then resize them at most this. Wait, this is LL, and yeah, so that should be cool. At minimum this, and then okay, so if opener.left is so what about if r is like, if there's no opener, would r be 0? So what here about there's no opener? Let's say here there's no opener. Would r be 0? Yeah, r will be 0. Okay. So open left is the opener, and then if if it's left over, then if there's no opener, then I need openers at op pointers. So I get opener, but I get leftover minus minus. So if leftover, and now there is an opener, then you want to buy what do you want to buy? You want to buy a regular, right? So regular at I, so you want to buy like happiness 1 plus equal regular at I. So I buy this and I say openers left minus minus. This is how I buy them, and this is as much as it's left over. So it's like it will come to a point when there's like no leftover, and that's pretty much it. And then the answer is max answer at H1, right? But okay, so we bought everything. Buy all PT cans priority, and then buy all of these. And then now I need to reverse my decision for some PT cans and then try to buy here some other things. So okay, so int r pointer here is I. This is the last thing I bought. This is the last thing I bought. And what is int p pointer is how many things I bought here. It's like this, the minimum of m. Can m be 0 though? No, cannot be 0. So the minimum of m and pt.size, so this is like how many things I bought, minus 1 is like, this is the last thing I bought. And then while p pointer is bigger or equal to 0, I want to unbuy this thing. So I want to unbuy pt at p pointer, get my leftover plus, so get my leftover a bit more, right? But then try to go and try to update the r pointer. And then I will have like some maximization of the answer. So the R pointer will be while R pointer is smaller than R dot size. R pointer plus 1 is smaller than R dot size. H1 plus R at R pointer. Now you see some mistake here, but so if this is like if leftover is 0. If leftover is not 0, then like here this is the maximum we can get, like because I have bought all of these and I bought all of these. And yet there's more left over, right? Okay, so the trick here is that while I can get the next number, are there cans left? This is very important. Are there cans left? And this is the same thing I will do here. So I will say like this, leftover is plus plus, and then try to update the R pointer, right? So we go and we say, okay, we can do this. If the cans are 0, we're gonna find the can. We're gonna find a can opener. We're gonna find the can opener, and we're gonna buy it. And then if it's left over, what I will do is I will get the R pointer here plus 1, and then I will say R pointer plus plus, and then I'll say leftover minus 1. So it's leftover minus minus, R pointer plus plus, OP left is minus minus. Then the P pointer has to be here minus minus. There has to be a P pointer. So let me just do this. Now the answer should not be correct, right? Yeah. But now if I do this, if leftover is 0, so there's no leftover, then the P pointer is the minimum of this here, how many I've bought. The P pointer is bigger or equal to 0, then I minus the happiness, I get away that P pointer. I put the leftover more, and then I go R pointer plus 1 is smaller than R size. If it's OP left is 0, so if it's like left of the openers, then I gotta buy more openers, and I gotta of course get the pointer up. then so I gotta get the pointer up here, and then the leftover is this bar out. Just 25. Hmm. 25. This is the last thing I bought here. Okay, I will submit it. Just let's just do one more case about well, and let's say that it's like 2, and m, let's say that it's 1, and then let's say that 0, there's a pull tab which goes like this, and then there's a can opener with, so there's like 3 items, and then there's like 2 of these, 0 and then 1, there's like more than that, and then there's 2 a can opener which opens like 1 item. This would be like that, but this would be 1000. I mean, I don't know, I hope this is right. I hope this is right. Let's see G. Gets accepted. So, okay, so let's see G. You're given a tree with n vertices. Find the number of tuples. The given tree does not contain a simple path that contains all of the vertices I, j, and k. A simple path that contains all of the vertices. Find the number of tuples such that the tree does not contain. So such that J is not a LCA of I and K. No, actually, yeah, no. So the J is not like in between I and K, right? Alright, so let's think about this. J is not in between I and K. And the number of tuples such that this is the case. It's a pretty cool problem. J and K. J is not tuples. If I fix J, then there are quite a number of tuples. So this is I want, if I fix oh no, so this is like from 1 to n to ijk. So if I fix j, if I know j where j is, I want to find how many in the same subtree of j, how many in the same child subtree of j, how many I and k's are there. Okay, that's one thing. And then the other thing is how many. So now, okay, so this is j. This is how many I and k's are in like the child subtree. Well, I can solve this with like persistency, but not the point. Not the point to solve it with persistency. Okay, let's go let's no, I will solve this. I'll solve this. So if j is here, I need in this subtree and in this subtree and in this subtree to find how many there are smaller numbers than j, how many are there bigger numbers than j in these subtrees, and then I need to find also in the parent subtree smaller numbers and bigger numbers than j. So in like without this, right? Let me just for it. Okay, so this is the idea. So okay, so in this subtree, okay, so we have some trilinearization, and then in this segment, how many numbers are smaller than j and how many numbers are bigger than j. This can be done in many ways. I haven't coded something like this in a while, but this is very straightforward. If B is B, if the B is parent, we just continue. Otherwise, with DFS and B with the U parent, very straightforward. Timer in, timer out. Very straightforward. Time in, time out, and then here time in resize and time in resize, time out resize. Okay, so we have this, and then now we want to say, okay, so we have this U here. The subtree of U is between these 2 points, between this time in and time out. So want some array here, like let's say this is like linearization, then linearization at timer is like U. This is the linearization at timer plus like that. So okay, so given this linearization, now want like we want for each of these n, I will have like a query where I have from this point to this point right? So we have an array, and then want to find how many integers are smaller than this guy and how many integers are bigger than this guy. Because they're up to n, we could have just done DFS, right? Like just a DFS, and then this, like, but no, you need persistency, because when you return back to this point, yeah, you need persistency. Okay, so I think this is an easier approach with the linearization. Then you have some integers here, and okay, what we want in range from time in of I and time out of I, how many integers are smaller / bigger than I. This is what we want. And this still can be done with persistency, but other than that, can it be done with, so for each I, we have to do this. Can it be done with, so in this range, yeah, maybe like square root decomposition would, I mean, use persistent sandwich. I don't want to use persistent sandwich. So let's just say that we have like most algorithm, and we put all of these queries into like one big one bucket, and then you want to have like two fanfic trees, and then that would be square root times log n, which doesn't really quite do you have time to do this? Probably. But is there a better solution than this? So one thing is how many integers are smaller than bigger than I, and one other range is like in range time in range excluding this time in I and time out I, right? This is like the other range. But wait, you need for each subtree to do this, right? You need to do this for each subtree, right? Is that correct? Yeah. So what about centroid? About like centroid decomposition. So what we'll say, the number of paths such that I mean this could be solved with centroid decomposition. Incredibly faster than what I'm trying to do. It's still unlocking. So for each node, we want to see how many nodes are paths that go through this node that have like smaller I and smaller. Yeah, that's another way of thinking about it. That's another way of thinking about it. Centroid decomposition at each. But I'm not quite sure. Well, you have to have like a fanfic, right? You have to have a fanfic here. then when you do a layer, what you do is this node, and then you no, you can't do sentry. Yeah, no, doesn't quite work. So the best solution is somehow persistent. It's persistence. Persistence is hard to code. I mean, I don't care about this. Persistence is hard to code. It's not that easy. When you come here, you have some. You do some persistence, and then when you go back, you undo this. I mean, you go back. It's fine. But when you go here, then you want to undo this. So okay, so what about like you merge them? What about you merge here smaller to like bigger? You find like you have set and you merge them and you go like this, and then you need to do one more DFS where you assign the bigger edges here. Okay, that could work. So that could work. So you have like a set. You want to merge the like this, and then you want to sets for each size. You want to push back the elements, and then set is 0. You want to push back. You want to insert U here, and then here you want to insert that, of course. And now I want to just I mean, this is not like, okay, this is a set, but you need an ordered set, right? This is gonna this is gonna be heavy, computationally heavy. Ordered set. Shit. Ordered set. Family tree of ordered. So we want to have these trees here, order sets, and then you want to so you have like, this is like the whole set. And then when you're here, you want to, for each of these sets here smaller than you, for each of these sets, so there's some like answer, and then for each of these set sizes, I want to find how many of these are smaller than so there's like there's a function I wrote there's a function I wrote how many are in an interval, and what you can do is you can call this function with sets at I, and you can do an interval from 0 to u minus 1. It's like k, and then there's like L here from u plus 1 to like n. There's L, and then the answer is k plus L, k times L. So this is not correct, but oh wait, fill. What is fill? Right. I'll need century deco. So this I don't need that. So tree. What? No, it doesn't have a type. Tree doesn't have a type. It doesn't have a type. You need maybe to import something. Okay. Tree doesn't have a type. Oh. But there's no return statement. Sets at I, sets pushback DVU. That's correct. Resize UV0 sets at I. Answer this. Sets at size. Set 0. Insert element 0. Insert U. Oh, if sets empty, set pushback just empty tree. Okay, I don't have time to fix this. Okay, so that works. And then you want to see out the answer, of course, but the answer is not correct because the answer doesn't account. Okay, so it finished. Okay, whatever. But the answer doesn't account for the up tree, so it kind of counts only for like down, but it doesn't account for like the whole tree from the other side. So that would be like one more DFS probably. But this is very suspicious here. I mean, it could be just constructed so that everything is on the other side. But this is not finished, so I don't know. Let's just read the tutorial if we are correct at this, or is there like very easy solution to this problem? Both paths, same side, with respect to I. Where V is fixed, suppose the rooted tree has a count over distinct subrooted at V. Okay, so distinct subrooted at V, okay. There's sufficient to it is sufficient given a sequence C, find the sum of the products of three distinct elements. This can be computed in okay, I don't quite understand what it wants to do, but I want to take a look at like some summation just to see if we understand. So the size, and then the so this is like these are all, and then all minus whatever we don't count. So what we don't count is the vertices such that this is on the one side and this is on the other side. I mean, okay. N minus up is n minus size. I mean, okay, it's based. Yeah, this is the magic sauce. What is the next vertex and the size of the next vertex in an array, and then you sort the array and then you calculate this. Okay, I understand. I kind of understand what's going on. And because this is like really quick here. That's cool. That's cool. That's cool. So what it does is actually like sorts the children vertices, and it tries to match which of the children like vertices can. Because the children vertices are smaller than him, all of the paths in the children vertices will also be smaller than him. Well, that's the kind of idea we want. Yeah, that's because it's a permutation. It's just a permutation of the n vertices. So it's not. This kind of simplifies the problem. Let's see just tangency of cuboids to. So okay, we have it's sufficient to inspect all pairs instead of cuboids. Specifically can be solved for prepare m by m. So this is what I said at the end. For all cubes, check which cuboid contain the cube itself and adjacent cube, and maintain the. For each cuboid, yeah, because they don't intersect, you need to, yeah. It's stupidly simple. We can solve this and the other problem as well. Because this is so small, you could, so yeah, so you need to check, because we know that it doesn't intersect, it doesn't contain one cube in another cube. It means that we're gonna go through the volume of each cube and see if somehow matches to some other cubes thing, and then if it matches it, and it's yeah. So that's stupidly simple to code. We can even call it right now just to. We can even call it, but I want to publish this as fast as I can, so that's why I may do like an upsolve video later for all of these. So let's just go through the problems once again really quickly. So I want to just talk about it, just like write these, and then I don't see a pattern here. Oh yeah, I see a pattern here. There's like A, B, C, D, E, F, and then G, and then there's like C, D, E, F, G, A, B, and then so yeah. So there is a pattern. You don't need to write this, but okay, it doesn't quite matter. B, you just have to check. You just have to check these 9x9 here thingies, but then there's like 4x4 thingies that I check, and then I only check for a dot if it's like on the edge, so on the third column or on the third row I check for a dot, and this happens as well from the downside. But what I do is I minimize. I start from here and I minus, so I go like I subtract it. And then this is why I say I plus 9, because this is I plus 9 is like this point here. Then minus k and minus 1. So I plus 9 minus 1 is like this point here, and then minus k is like where this point is in the row like this, and then where it is in the column. And because there are squares, you don't have to worry about like here indices, and just you have to worry about that these are dots when this is equal to 3. And then when it's otherwise, it's like this have to be hashtags. So it's pretty simple. C was like the same simple problem. The trick is here that how C looks in monotonic. So some people start some people will sell the product for at least some amount of money. So like, let's say the money is on like a number line, right? And then some people will start selling the product from like here. Like this. And some people will buy the product at most like this. So here, let's say like this. And what you can see is that first you have a lot of people that will buy the product, but there's no sellers. And then it starts gaining sellers, but starts minimizing the people that will buy the product. So it starts like, okay, so there's like buyers. What am I doing? Buyers. And then there's like, technically, like it's like this, like, okay, let's write here sellers. And here let's buy buyers. So there's a lot of buyers at the beginning, and then here it goes. So the trend is like this. Okay, so you have here, it pops up -1 buyer, right? Here, oops. So here it pops up -1 buyer. Here it goes to up a seller. So the seller goes up here. And then the buyer goes minimizes it, and the seller, and here the seller maximizes. So the buyer essentially does like fall down, and then the seller rises up. And we want to find a point where, here this point, where the sellers overtake there are more sellers than buyers. And what you can do is binary search in which point that will happen. So L here is an invalid point, and R is for me a valid point. And we know that if R and L are bigger than 1, their difference, we're gonna do this. So binary search. The midpoint, we find the midpoint, and we count how many sellers will sell if the midpoint, if the midpoint would be the cost of the product. So the cost of the product would be like, okay, so if the sellers are like, if the cost is bigger than this, then the sellers will sell it. How many buyers will buy this product? So the buyers will buy if the cost is smaller than some BI, right? Some here amount. And we want to find whether or not the sellers are more than the buyers, more or equal than the buyers. And this is where this is a valid statement, and this is invalid statement. What I'm saying by this is this here will execute when this is valid, and we want to minimize the R. We want to move the R because we want to minimize. We don't want to maximize the thing. We want to minimize. So we want to find the smallest point in which that will happen. So R has to go to the left side, and otherwise L has to go to the right side. But when L is changed, this is still not valid L, because the sellers are smaller than the buyers. And then at the end we just print R, because R is valid. R is always going to be valid. If there's more seller and there's what buyers, and R is valid. So yeah, that's pretty much it for C. For D, you just have to see this DP, where the DP state is what here I wrote, is the DPI of n balance represents if I'm in index I and I have some balance till the index I, so till some index I, how many combinations of this are possible. So if I have some balance up to here that is equal to +3, let's say that balance up to here to this index is equal to +3. Let's say that I have like something like this, and this is like +1, -1, +1. No, this is +1, -1, -1. plus 1 plus 1 plus 1. Then this is like index, this now has 3, this is a balance 3. At this index I has a balance 3. This is one possible solution. There could be some other solution, let's say something like this, maybe something like this, I'm not quite sure, but no, something like this. This is 3 as well, right? This here, and the 3 are left. So how many possible solutions do they give this balance with this amount of index already spent? And when I receive this or this, the balance only goes up and down. But when I receive the question mark, what it happens is that now it gets duplicated from DP, from the previous DP with a bigger balance. I can choose to make it now smaller, and then, or if I had from the previous DP a smaller balance, I can add like this bracket. I can add this bracket to make the balance bigger. And this is essentially what I'm doing. If it's a smaller bracket, I take the small, if it's an opening bracket, I take a smaller balance and I put it in myself. Then if it's a closing, I take a bigger balance, put it myself, and if it's like a question mark, I see both of these and add them up, and then at the end I want to have a balance of 0 to be a valid sequence. And at the end, the last element has to have a balance of 0. So quite a straightforward DP problem. I like this problem. Yes, as we discussed so we had just to see these constraints here that up to 100. I will solve this problem, but you essentially go over all of these volumes and you check if some volume kind of intersects with some other volume here, and yeah, quite an easy problem to code, but I didn't see this constraint until very late, and then I didn't quite know. I projected this problem into this space, thinking that 2D space will solve this problem quite faster, but it was a lot of code to try to implement this. Problem F was a greedy problem because you could formally prove some things over, and I did explain everything in my if you go back into the F, I did explain how I first pick up this pull tap cans. I buy them as much as we can, then I buy as much as, like with the leftovers, I buy as much as of these R cans as we can, with like the openers always sorted with like the biggest opener. This, if it's like, if it can open 5 cans, then this 2 cans, and then this 1 can open. I just delete the other like things here that can never be bought. There's not enough openers to buy them. And we can prove that the biggest opener should buy the biggest, should open the cans with the, so the opener that lasts the longest should open the cans with the highest happiness value. And you can prove it on many other ways, but with the exchange principle, it will be never good to exchange something like this to open some other can from here, because all cans are equally worth. So like one of these cost values. And we have M of this. So I buy first of these like pull tap cans, and then I try to buy as many R cans. But then let's say we succeed buying some R cans. Let's say that like I have I have some limited amount of M, so I buy this. Of course I need to buy this. Let's say I buy like this. And then now when I have bought these cans, I can now try to see if I can exchange one of the pull tab cans. So I just delete one of the pull tab cans into one of the art cans, and this could sometimes make me a bigger profit. And all of these are sorted in decreasing order. The R, the pull type, and this are sorted in decreasing order. And one can prove why is this optimal, because of the greedy principle, the equal cost of all cans. And this is just like pointer work, so I won't go over how I implemented this problem. This is probably not the best implementation out there, far from the best implementation, but you kind of see quite things, and I explained this while I was coding it. Of course, G, I won't comment a lot on G. I had 4 different solutions, and I started writing this solution with the merging smallest to biggest, but apparently it just seems to have a way easier solution, and doesn't require these complex order set data structures that I'm using here. Yeah, so this is it for today. I will upsolve these problems maybe in just like future video, but for now I'm maybe going to go on Google Forces, and there is a division tool round as well. So yeah, thank you guys so much for watching, and I see you in the next week. Yeah.